All right, I'm going to continue our ghetto lesson here on kinetics using some questions out of the textbook. I really wish these were available on WebAssign, but that's okay, whatever. The best way to go through this to get the most out of it is when I say stop the video and think about it, if you actually do that. And then I'm treating this as kind of just a discussion. And so I've got some questions here, and I'm going to answer the questions in hopes that you've thought about it, and then my answer will maybe jog some additional neurons. And I think I mixed a metaphor. Oh well. All right, so question number 10 here. The activation energy of a reaction depends on the overall energy change for the reaction. Why is that false? Okay, well, think about what that we did those energy profiles. The activation energy is just the distance above the reactants. Okay, so we did our energy profile, and there's your activation energy. So if we were to take that and start kind of at the same level, what if it was endothermic? Would that change the activation energy? The answer is no, it wouldn't. Okay, your total energy change, I think I actually, now that I'm thinking about it, I think I misspoke in the last video. So if this were your delta H here, then the total energy change would be the sum of those two, and that would be a very large number. So really your activation energy is what it is. It doesn't matter what your overall delta E. That's just dependent on the change in levels between your products and reactants. Part B, the rate law for a reaction can be deduced from examination of the overall balanced equation for the reaction. Now this is very important. The answer is you cannot. Okay? If I just give you a reaction, and there's 2, 3, 4 reactants, and there's coefficients, you cannot assume the coefficients are going to be those orders that we talked about. You have to go to the lab. Most of kinetics is lab-based. Now, as we get into these mechanisms very soon, we'll make an exception to that, but that's special. But overall, no, you cannot do that. You have to do it from the lab. Part C, most reactions occur by one-step mechanisms. Yeah, there's no most to that. Most, there are lots and lots of different mechanisms. Some of them are 2, some are 3, some are 4, and some organic reactions can be pages long. That's what makes being an organic chemist and developing pharmaceutical drugs is such a high-paying and expensive proposition. Those steps can be multitudinous, like you wouldn't believe. I can't think of an example off the top of my head, but yeah, really 10, 12, 20, 40, 50 steps are not uncommon. All right, number 11, define what is meant by unimolecular and bimolecular steps. All right, so this goes back to the collision theory. So the collision theory tells us that we have to have collisions to make reactions go. So a unimolecular collision is just when you have one molecule, literally one molecule, and really it doesn't have to combine or collide with anything. It just breaks apart. So that would be like your decomposition reaction, just one molecule. Now bimolecular is more of the traditional collision theory. Bimoleculars, just you need 2 things that have to collide, okay? And that's it, just 2 things, bang. Now it doesn't have to be 2 different things. It could be 2 of the same thing. If 2 H's come together to make H2, that's still 2 things that have to hit, so that's still bimolecular. Beyond that, we have termolecular, and then it progresses. It's really fascinating when you dig into the higher order math here, the statistics, the statistical mechanics that are involved in this stuff. You start seeing the numbers about the probabilities of these collisions being successful, and they can be mind-bogglingly small. When you get up to termolecular steps, which means you have to have 3 things collide, and those 3 things have to collide, all 3 having enough energy and all 3 hitting in the same orientation, well, now your probability of a successful collision really drops. I didn't say it was impossible. I said it really drops. I mean, it's small. It's so small that many textbooks say that it's impossible. It's not impossible. It's just really hard to do. And when you get above termomolecular, now you start getting into like winning the lottery type stuff, if not even worse odds. So really, unimolecular, bimolecular steps are the only ones that we can get. Termomolecular under extreme circumstances, usually with a little help from a catalyst. And that will lead us into the necessity of doing reactions in steps. Instead of, if we have a big reaction where there's 3, 4 reactants with lots of coefficients, it's probably not going to all just smash together at one time. It's going to happen in steps. So number 12, the plot below shows the number of collisions with a particular energy for 2 different temperatures. So the question goes to the top of the next page. But I want you to notice, do you recognize that graph? I hope you do. That is a Maxwell-Boltzmann distribution that we did back in the gas laws. It's back. It's coming back. So just take a look. We've got a tall T1 peak, a short T2 peak that kind of flattens out, broadens a bit. And the question at the top, you don't have to see it. I can read it to you. Which is greater, T2 or T1? In other words, what's the higher temperature? Well, I hope you very quickly said T2 is the higher temperature. A student doing this quickly and carelessly would have said T1's higher because it's the peak, it's a taller peak. That's not what the y-axis is. It's the number of collisions. So we know it's the higher temperature because we can see that a larger fraction of the molecules are going to have the sufficient energy to overcome activation that we need. At a lower temperature, you have a smaller percentage of the molecules having that sufficient energy. And then part B says, what does this plot tell us about the temperature? I just went over that. All right, moving on. Number 13, find for the reaction of oxygen plus NO goes to NO2. Let's see if we can get the focus just a little better here. The observed rate law is rate equals NO, and I know that's very hard to see right now. That's a squared and then times the molarity of oxygen, or partial pressure. It should be molarity. Which of the changes listed below would affect the value of the rate constant? Would increasing the pressure of oxygen gas change the rate constant? The answer is no. It will change the rate, but it will not change the rate constant. So think back to Algebra 1, y equals mx. If you change the value of x, that changes the value of y, but it doesn't change the slope of your line. So that's the same thing we're saying here. So the answer to that one is no. Would changing the temperature? Absolutely. Absolutely. Changing the temperature does things in chemistry. So we would definitely get K is only valid, it's only a constant technically as long as the temperature is constant. And then using an appropriate catalyst. Yeah, catalyst would have no effect on K. It'll affect the rate, but it won't affect K. All right, we're going to skip 14, 15. Table 12.2, which I have no idea where that is, illustrates how the average rate of reaction decreases with time. Why does the average rate decrease with time? So that's a very important concept. Why would the rate of a reaction decrease with time? Most of you think that should be constant. It's a rate constant with K. It doesn't work like that. The rate constant represents that gradual change as well. So think about it in terms of collision theory. When you put 2 reactants or 3 reactants together, they have to collide to react. And we've just learned that collisions are the key. These molecules and atoms have to collide. Well, when is that the easiest? Well, at the beginning, when there's more of them. So as the reaction progresses and you start losing molecules, your concentration goes down of your reactants, then the frequency of those collisions is going to drop. They don't hit as often. And so your rate of reaction decreases. As the reaction progresses from reactants to products, it slows down. At some point, it could slow down to the point where your products will actually start going backwards and reforming the reactants at the same rate. And when that happens, we get what we call equilibrium, which is coming. How does the instantaneous rate depend on time? So we talked about that earlier. So the instantaneous rate is just when you pick up a very specific time, we've got to go up and we've got to do the slope of a line tangent to the curve, or if you know the function, which is your rate law, you can just take the derivative and get that. We are going to use some calculus here after Christmas. All right, I'll skip 16 for now. Number 17, the initial rate of a reaction doubles. Oh, here's one of my questions. The rate doubles as the concentration is quadrupled. What is the order of this reaction? So think about that. The initial rate doubles as the concentration is quadrupled. So basically what we need to figure out is 4 to what power gives you 2? And to me it looks like a 1/2. So here the order of the reaction would actually be 1/2. I told you it happens. If a reactant has a -1 order, what happens to the initial rate when the concentration of that reactant increases by a factor of 2? So a -1 means you have a bit of an inverse. Well, it's not a bit, it is an inverse. So if you double your concentration, you're going to half it. You're going to actually half the rate. Yeah. Let's see. So number 18, hydrogen reacts explosively with oxygen, but a mixture of hydrogen and oxygen can exist indefinitely in a room. Yeah, they don't just magically explode. Just like gasoline, you can have gasoline sitting in a can, but there's oxygen in the air. It doesn't just explode and start burning. Why do hydrogen and oxygen, or even gasoline and oxygen, not react under these conditions? So the answer is you have to overcome the activation. So these collisions are happening, but as long as the temperature is normalized, they don't have enough energy when they collide to overcome the activation, so you're safe. But if you light a match, oh boy, so now you light a match and you are energizing some of those nearby molecules that are absorbing the energy from your exothermic match strike, and now those molecules have enough activation energy, and so now they collide and it goes, and that creates more energy, and that energizes the others. It's basically a chain reaction that happens, as you've all seen, extraordinarily fast, but that's it. You have to have the spark. Same thing with a fire triangle you learned in elementary school. To start a fire, you have to have fuel, you have to have oxygen, and you have to have the spark. And it was too young for you to know at the time, that spark is chemistry. It's overcoming the activation energy. All right, I guess, let's see. Number 19, the central idea of the collision model is that molecules must collide in order to react. Give 2 reasons why not all collisions result in product formation. So I went over that. Think about it. What did I say? Two things. I said that when collisions happen, they have to be in the correct orientation, and they have to have enough energy to overcome activation. And finally, number 20. Number 20 is a bit of a reach, but we'll do it anyway. Consider the following energy plots for a chemical reaction when answering the questions below. So which plot is the catalyzed pathway? Okay, so what a catalyst does is find a pathway for a reaction that makes that activation barrier easier. So as you look at this graph, and I know you wouldn't know this, but that's what I'm telling you now, this blue line is the catalyzed pathway because it's easier. Catalysts lower the activation energy, and that is a very, very common multiple choice question. Catalysts work by lowering the activation energy. Or really what it's doing is it's finding an alternate pathway that has a lower activation energy. What does E1, delta E1 represent? So let's find E1. Okay, so that is this giant line right here. That represents the activation energy. for the uncatalyzed reaction, all the way to the top of the purple. Reactant level, all the way to the top. What does E2 represent? E2 represents the enthalpy, or the change in internal energy if it's no work being done. Same thing. And is this reaction endothermic or exothermic? And I hope you said endothermic. We are raising the energy level of the products. All right, well, that was a good question, sort of, / discussion to kind of get you thinking about kinetics. So, yeah, if you have any questions, email me or ask me when I get back to class on Tuesday.